Today's prep day. Exam on Thursday. Exam number 2. So exciting. The one big change on here is that we are passing on this stuff. Since we had our one missed day, we're going to ixnay that, which is fine because all of you that are going on will eventually take differential equations and you will miss nothing. Just a very brief introduction to differential equations. It will not be like missing anything important. In differential equations, they start from scratch no matter what. So these ideas will be there waiting for you.
Isn't there a class for differential equations?
Say that again?
Isn't there a course for differential equations?
Yeah.
Yeah, so it's just okay.
Yeah, we never used to cover this in this class anyway, and then the system office decided that we should at least cover an introduction, which we never totally understood because anyone taking Calc 2, there's a few exceptions if you're an architecture major or something. There's some Calc 2 students that don't go on, but anyone that's going on to engineering is taking that anyway. Anyone that's going to use differential equations in their job is going to take differential equations. So it is no big deal at all to pass on those 2 sections in this class. So our exam will be all of Chapter 8. And standard stuff, no graphing calculators, no calculators with an integral button, no phone calculators, that stuff. So let's just start. We'll take a look. We'll take a look at all the topics that we've covered and figure out anything that you have questions on. This test tends to be a little bit easier than the last test because it's less conceptual. It's a little more procedural based, so that's kind of cool. And then we have the gauntlet coming up next, infinite series. So, is that big enough back there? Can you see that? Yeah, you can see that back, right? That's. All right, so this is a classic reverse chain rule type of problem. You could use substitution if you wanted. And generally when we're using substitution, we would say, let's let u be whatever's in parentheses, whatever's in a square root, whatever's in an angle. But we have this one shortcut. If that substitution happens to be linear, instead of going with substitution, we can go directly with RCR, reverse chain rule. And that's a nice thing to understand because it saves us about 4 or 5, 6 steps depending on the substitution. So because that's linear, we can immediately cut to the chase. We can add 1 to the exponent. So we're going to have 2x minus 1 to the negative 3. So add 1 to the exponent. We'll divide by the new exponent. And the reverse chain rule part says, take the derivative of your base, so what's in parentheses, and divide by that also. And then we'll have our constant of integration. So that would be integrating using reverse chain rule. So power rule first, add 1, divide by the new exponent, and then divide by the derivative of the substitution or the base. And so if we simplify this, we would normally write this as negative 1 over 6. We generally try to get rid of negative exponents. So that would be our final. Any questions on that?
Remind me when you have to multiply the negative 3 with 2.
So this piece right here is for the power rule. When you add 1 to the exponent, you always divide by the new exponent.
Right, with the reverse chain rule.
And then the reverse chain rule says take the derivative of this and divide by whatever its derivative is. So if we have something like the integral of e to the 3x plus 1. Again, that could be done with substitution, but that's linear, so we don't have to use substitution. The integral of an exponential is itself. And then the reverse chain rule, we would divide by 3 because that's the derivative of the exponent. So that is another example of it. And the other place we see this quite a bit is if we are integrating an angle. So if we have something like the integral of 7x dx, same thing. The inside, we can make this even more complicated in here as long as it's just linear. So if this was, say, 7x plus pi dx, the integral of cosine is sine, and because that's a linear angle, we could do this with reverse chain rule, and we would have that. So as long as what's in the exponent, in the angle, in the parentheses is linear, we can always do this reverse chain rule piece. Another classic one that we see with reverse chain rule, if we were integrating the square root of, say, 4x minus 1. I guess I don't need parentheses on that. So if we have something like that, same thing, we can think of it as a substitution if we wanted. We can make that exponent a 1/2. So it's very similar to the first one. The base, what's in the parentheses, what's in the root, it's all linear, so we know we can use reverse chain rule. So this will be 4x plus 1. We add 1 to the exponent, that's 3/2. Divide by 3/2 means multiply by 2/3. And then we have to also divide by 4, yeah. Yeah, we'll multiply the 3 in the denominator by 4. So we would end up with 4x plus 1 to the 3/2, all divided by 6 plus c. So those are all classic reverse chain rule types. Any of those give you pause? Makes sense? As long as that substitution is linear, we'll go reverse chain rule. Make sense? Yeah. Cool beans. Let's go to an integral with negative exponents. So the trick, if you will, is to eliminate negative exponents, and there's a few ways you can do it. The simplest way is to multiply by 1. 1 is our magic bullet. If we multiply by 1 in the correct form, that's usually the simplest way. And our target, we look, and there's this one negative exponent here, and we want to get rid of that negative exponent, so we're going to multiply by e to what power?
4x.
So e to the 4x, up and down, top and bottom, numerator and denominator. In the numerator, e to the 4x times e to the 4x becomes?
E to 0, which also becomes 1.
In the numerator.
Oh, numerator. E to the 8x.
E to the 8x, yep, exactly. And then in the denominator, what you said, e to the 4x times e to the negative 4x is e to the 0, which is 1. So these two, when we multiply those two together, that becomes 1. You add the exponents, e to the negative 4x times e to the 4x. You add those exponents, you get e to the 0. E to the 0 is 1. And what form is this in? Log form, right? Log form, you could use substitution if you want and let u be the denominator and go through substitution. But we've seen that when you have log form, you can cut to the chase. Log form is when the denominator's derivative is the numerator. So I need to throwing an 8 into that numerator so that the numerator is exactly the derivative of the denominator. But if we put an 8 there, we have to put a 1/8 out in front so that we've multiplied by 1. If you multiply by 1, you don't change value, you just change the appearance of it. Now it's in log form. And log form is nice because we know how to integrate in log form immediately. We don't have to do substitution. It's always natural log absolute value of the denominator. So that would be our final. Yeah?
So I had a question on when you're writing the natural log form. Because I've been having troubles with my MATLAB when it's asking when I write the natural log form on just the absolute, and then the right answer has to be a parenthesis. Like, how do I know if it is going to be the absolute or just parenthesis?
So if you have something like this, here you get natural log, you have to use absolute here because what's inside here could be negative. And we know that the log is, if we look at the graph of the logarithmic function, the graph of the logarithmic function looks like this. And so the logarithmic function has domain right of 0, so we can't put a 0 or a negative inside there. So if what's inside there could be negative, we need to use the absolute values. So if we have something like this, where let's suppose we have something like, let's make this x squared plus 1, and the numerator, let's just suppose, is exactly 2x. So now it's in log form. The derivative of this denominator is the numerator. So this will be natural log absolute value of x squared plus 2, but x squared plus 2 is always positive, so we don't need absolute value bars there because that's always positive. So if what's inside here is greater than 0, therefore no absolute value bars.
And can that be verified if you plug in something into the variable?
Yeah.
If you plug in a number, okay.
Well, yes and no. I mean, you need to, like here, if you plug in a negative, you see it's negative. Like here, it's a little less obvious. You have to plug in the right. Like if you plug in 0, e to the 0 is 1, so 1 minus 3 is negative 2. So you have to, if you plug in the right thing, you'll see if it's positive or negative.
Okay.
Like we know a sum of squares is always positive.
Okay.
Right? But if we had an odd power on x, then it could be negative if you plugged in a negative.
Okay.
So if you plug in the right value, you can see that it could be negative. Then you have to leave the absolute value bars.
Okay.
Yep. So then we had this clever technique when we have a quadratic in the denominator that's not factorable. If it was factorable, we could use PFD, partial fraction decomposition, and break it into two little fractions and integrate easily. But if we have a quadratic that's not factorable, and it's got this middle term, we also have some special cases if we had x squared plus a squared or x squared minus a squared. We have the inverse trig stuff. But if we have a quadratic, a trinomial that's not factorable, we did this technique by completing the square. And so here we look and we say, okay, we want to take these two terms and complete the square. We want to create a perfect square trinomial. We want that to be a perfect square trinomial, and so our technique for that is completing the square. We take the coefficient of x, divide it by 2, square that result. When we divide negative 2 by 2, we get negative 1. When we square it, we get 1. So we know to complete the square, we need a 1. So we just sort of borrow that from the constant. We take it out of the 50, and that's going to leave us with a 49. Then we actually factor. So in the denominator, we are going to have x minus 1 quantity squared plus 49. And this has the form of an inverse tangent. it has the form of an inverse tangent, and the way we've been doing this is to factor out that constant and make that denominator a sum of squares, in this case with a trailing 1. So we're going to factor out that 49. And if we factor out a 49 from something that doesn't have a 49, we use our magic bullet. We multiply by 1. And so then this 49 gets factored to the denominator, and we have x minus 1 squared over 49. But we don't want this term written like that. We want to write it as a single square. So we have one more step before we're ready to do the integration. We really would prefer, and most of us are going to do this in one step, but just to sort of highlight it, we want this to be a single square right here. And now it's in perfect inverse tangent form. So now we'll just couple the fact that we know that this is inverse tangent. We know that what's in here is linear, so we can use reverse chain rule. So then it all just comes together really nicely. We're going to have 1 divided by 49. I'm going to leave a little gap right here for the reverse chain rule. And we know that we are going to have inverse tangent of whatever is inside the parentheses there, plus c. What is the derivative of the quantity in blue? 1/7. Does everyone agree with that? So if we have this function over here, x minus 1 over 7, if you wanted to, you can imagine it in mx plus b form. And so that derivative is the coefficient of x, which is 1/7. So the reverse chain rule says, take the derivative of what's inside the parentheses here, divide by 1/7, which will mean multiply by 7 over 1. Reverse chain rule. And so our final answer will be 1/7 multiplied by inverse tangent of x minus 1 over 7 plus c. Guitar?
Question. So on MATLAB, instead of doing it that way, they do it where it's like x squared plus a squared equals a tan theta.
Not a tan theta. 1 over a inverse tangent of x over a.
Well, it's like how it does on there.
Mm-hmm.
Wish I could show you. But
Are we talking about trig sub or direct integration to inverse tangent?
it's trig sub.
Okay, so for trig sub, yeah, you're gonna, so this is not trig sub though. So for trig sub, you would let u equal a inverse tangent of x, right? Is that what you're talking about?
Yeah. Okay.
So, but this is not trig sub. So if you were doing this using the technique they have there, you would say a is 7. And you would end up with 1 over a, and then here you would have your x over a. Which, and you can do it that way, you just have to remember where all the a's go. And so my point is that if you always make this a 1, you never have to think about a. You never have to figure out, oh, x over a, some of them have a 1 over a in front, some don't. Like inverse sine doesn't have a 1 over a in front. So you don't have to worry about that. If you always make your constant here a 1, you never have to think about it. All you need are your basics. So you know that the the integral of this is arctan. So if you know that and you know how to do reverse chain rule, you never have to think about the a. You never have to remember. And similarly, if you do the one for inverse sine is going to be the integral of this. And then, of course, there's the inverse secant, but that one's way less important. These are the important two. So here, if we can make this a 1 or make that a 1, and we know how to use reverse chain rule, we don't even have to think about Like in 5 years, think a few years down the road, will you remember where you put a 1 over a? Probably not. But if you can remember your two basic integrals and you understand reverse chain rule, which you could always do substitution. If you forgot reverse chain rule, you could always go back to substitution. And right here you could say let u equal x minus 1 over 7. And then you'd end up with a u squared plus 1, so you'd be back in this basic form. So if we look at the basic forms and then couple it with substitution or reverse chain rule, then we just have to memorize less in the long run. Does that make sense? So that's why I do it this way. You know, the books, they're going to always do it with the memorize as many possible things as you can possibly memorize way, which in the long run is not a great strategy because it's just so hard to, why remember 6 things when you only have to remember 3? And this technique of substitution or reverse chain rule is so important that doing it this way also just keeps reinforcing reverse chain rule. Because we see it repeatedly through Calc 2 and Calc 3, where we've got this linear expression here. And getting efficient at integrating when there's a linear substitution is just going to make you way more efficient at integration in this course and in Calc 3. So that's kind of why I target that. If we can get to the 1, it's just a little easier.
Remind me again, where do you get the 7 over 1 when you multiply the 1 over 49?
The derivative of this.
Okay.
All right, so x minus 1 over 7. This is linear. The derivative is the coefficient of x.
Okay.
So if we divide by 1 over 7, we multiply by 7 over 1.
Okay.
So the reverse chain rule says divide by the derivative of whatever's in your parentheses.
Okay.
Now, one thing, Katura, here, you also, if you forgot that this is inverse tangent, you could use trig sub. You could use trig sub here and say, oh, let's let tangent of theta equal this. And it would all come out in the wash. Like if right here, so let's just suppose right here, we didn't remember that that was arctan, but we do remember that trig sub for tangent is when you have a plus. You could say, oh, let's let tangent of theta be x minus 1 over 7. So then the derivative of tangent is secant squared. So you could take your derivative right here, and this would then become 1 over 49. dx would be replaced with 7 secant squared of theta times d theta. I'll put the d theta to the right. And then the denominator becomes tan squared plus 1. And what is tan squared plus 1? Secant squared. So then these guys cancel. That and that cancel. And so then when we do our integration, the 7 comes to the front, giving us 1/7. And we have just the integral of d theta. And what's the integral of d theta? So then we go back up here, and theta is inverse tan of x minus 1 over 7. So we could do it that way if we totally...
Yeah, that's what I meant.
Yeah.
Because they have it in there where they have it where it's like a tan theta something.
Mm-hmm.
Yeah, so that a tan theta is right here if you multiply both sides by 7. Then you would have x minus 1 on the right and a tan theta on the left. So when we have this basic integral here, ideally you see right here that it's in arctangent form. You don't need trig sub, ideally. But if you did trig sub, it's no big deal. It will work. All right, let's go to integration by parts. Integration by parts, we think of it as a way to integrate a product. We think of it as a parallel product rule thing. You have your product rule when you're taking a derivative, first derivative, second, etc. This technique of integration by parts sort of reverses the product rule. It allows us to integrate a product. It allows us to integrate a lot more, but at its core, we're integrating a product. And and we need to use this formula. We need to separate the integrand. We need to identify each of those two pieces. We need to identify a u and identify a dv. And then once we've identified those, then the integration by parts formula is our ultraviolet voodoo, uv minus the integral of v du. Ultraviolet voodoo. So there's usually several ways that you can arrange your u and your dv. Often only one works well, though. So here's a classic case where if we were to put the x over here, this would not work. So if we did this, that's not going to work, because when we integrate here, we get x squared over 2, and we would end up making an integral that's more complicated than the original. So if we do uv, that's fine. But if we integrate v du, notice that the power on x has gone up. And so that's not going to work that direction. That's going to make the integral worse. So in many cases, there's only one option that's going to work. And in this case, we want the x to go here and the e to the 4x to go here, so that when we differentiate, we get du equals dx. And when we integrate here, we'll get 1/4 e to the 4x. And now we see that this integration by parts, this choice for u and this choice for dv, the power in x is going to go down. So we're going to end up with u times v, so that's 1/4 x e to the 4x, that's uv, minus the integral of v du. Okay. All right, so uv minus the integral of v du. The ultraviolet we already did right here. uv minus the integral of v du is the bottom row, so minus the integral of 1/4 e to the 4x dx. This now has an integrable integrand. We don't need anything special there, so we end up with this term out in front. This is an exponential, which we can integrate with reverse chain rule. So the 1/4 stays out in front. I'm going to leave a little space. The integral of an exponential is itself. So there's the itself part. And then the reverse chain rule piece says, oh, the exponent's not just x, so we need to make an adjustment. So we look at that exponent. It's linear, so we can do reverse chain rule. Its derivative is 4. We divide by that 4. So there's the reverse chain rule, division by 4 right there. So that part's RCR. And so this simplifies just a tiny bit. Any question on any of those steps? So integration by parts, the big checkpoint is right here. If the integral is easier, you're on the right track. If it's harder, go back and start over. If it's equivalent, then we're probably doing the integration by parts with a twist, where you have to do one more integration by parts, and you have to do that algebraic thing where you add the integral to the other side, the twist. All right. Let's go to integration by parts with a twist. So integration by parts with a twist is most commonly experienced when you have your product consisting of an exponential and a sine or a cosine. And the idea is that regardless of what you pick for u, what you pick for dv, you get this circular derivative thing happening. So e to the x, whether you differentiate or integrate, it's still going to be e to the x. Cosine, whether you put it with dv or u, as you integrate or differentiate, you keep coming back to cosine again and again. So it's got a cyclic derivative or integral nature to it. That's usually when we're going to end up with this integration by parts with a twist. Usually we want to call it something. The book will call it I. I'll call it omega. And then we go through the same process that we've been going through. And it doesn't really matter what you pick for your u or your dv. This is your personal preference. If it's easier for you to differentiate a trig function, then put the trig function over here and put the exponential over here. Sometimes you're more likely to make a mistake integrating a trig function because you get the negatives in there when you integrate sine. So if you're worried about that, then put the trig function over here with u. So the derivative of cosine. So we know the derivative of cosine is negative sine. So we're going to end up with negative 2 sine 2x dx. V will be 1/3 e to the 3x. So that is our first integration by parts. So the integral, we'll call it omega, is going to be ultraviolet voodoo, so uv minus integral of v to u. So 1/3 e to the 3x cosine of 2x uv minus the integral of v to u. Oh, that's now going to be positive, though, because v to u is negative, so it's going to be positive. And then we multiply the constant, so we get 2/3 e to the 3x, trig function, sine 2x. And so here, if you wanted to, you could factor out the constant, but what I've sort of demonstrated a few times is that if you leave the constant in, it's actually easier. If you factor the constant out, you're going to end up with these big brackets, and then inside the brackets, you're going to have an ultraviolet voodoo, which then will need a distribution in the end. If you keep the constant inside the integral, it avoids the big brackets, and it avoids the distribution at the end. So it's generally easier. So we're going to do a u and a dv, and we want to be consistent. If we let u be the trig function originally, then we want to let u be the trig function going forward. So I'm going to treat this product as this block right there, that factor, and then as this factor. And that 2/3, you could group it with either, but I'll just stick it with the exponential. Does not matter where the constant is. So 2/3 multiplied by e to the 3x. And for dv, we're going to go sine of 2x. Oh, whoops, I said that we were going to do the trig function with u, and then I didn't write it with u. So sine of 2x and 2/3 e to the 3x times dx. Okay, so this is going to make du, derivative of sine is cosine, so we'll get 2 cosine 2x times dx. And then here, when we integrate, we're going to get 2/9 e to the 3x. Is there any question on that integration by parts recipe over there? That's going to be our recipe down there. Those are our ingredients. So here, this whole integral is going to be replaced with an ultraviolet voodoo. So uv from here looks like 2/9 e to the 3x multiplied by sine of 2x. So there's the uv, the ultraviolet, minus the integral of v du. So v du is that bottom row, so that's going to be 4/9 e to the 3x cosine 2x dx. Any questions on those? And this stuff is all going to come down with us. I should be able to paste that, right? How do I activate the paste without going to the computer? There must be a way to activate the paste without going to the computer. So this becomes over here minus 4/9, and what we recognize is that, oh, right there, the integral of e to the 3x cosine 2x, that's back where we started, right? That's omega, the integral of the green part. So now we have negative 4/9 omega over here on the right. And on the left, we can rewrite this omega as 9/9 omega so that we have the same denominator, and then we can add from the right to the left. So this is the twist. We're twisting these omegas together, so we're going to have 13 omega over 9. That's going to equal the same thing over here. We're going to have that guy right there. And here's where we want to put in our constant of integration. The omega is an indefinite integral, so it's got a constant of integration in it. So as soon as we move this away and put it on the left, we have to make sure that we know this integration, this indefinite integral, needs a constant on the right-hand side. So we want to put in our constant right away as soon as we move those omegas, as soon as we twist those omegas together. And then our final step, back to algebra 1, we're just trying to isolate omega, so we're just going to multiply by 9/13. So we're going to multiply through by 9/13, and that will give us our final result over here. So that will be omega.
Can you do the first step again of the bringing the omega fraction?
Bringing this over here.
Yeah.
So we're adding 4/9 omega to both sides. So we want to make this and this have the same denominator. So we're just multiplying that by 1. And so then we add 4/9 to 9/9, we get 13/9. And then we're going to multiply by the reciprocal. So here we multiply both sides by 9/13 to get rid of that. So then this side gets multiplied by 9/13. So we distribute that 9/13 to each of those terms. And then 9/13 times a constant is just a constant. So we keep that as a C. Other questions on that? Yep.
So you said that integration by parts with a twist is usually when it's an exponential and a cosine or a sine?
Yep.
Okay.
The other place that we saw it this semester was when we had secant cubed. When we integrated secant cubed, we could put a secant squared with the dv and a secant with the u. And we could integrate secant squared and get tangent. And you could use, so we have that in our notes somewhere, you could do integration by parts with a twist with that. 99% of the time you see it with an e to the x and a cosine or a sine.
Okay.
Yeah. There was that one oddball situation. Okay, so a volume for a solid of revolution. Find the volume of the solid that's generated when e to the negative x. So here we're dealing with an exponential decay function. So e to the negative x, okay, goes through 0, 1 like all basic exponentials. So e to the negative x looks like this, horizontal asymptote. And we are going to look let's see. So we want to look at f of x equals e to the negative x, the x-axis, and we're going to be on the interval 0 to natural log of 6. So 0 is right here. Natural log of 6, we'll just claim that it's right there. And we're going to rotate around the line x equals natural log of 6. So we are going to rotate around this axis right here. So we're going to take all of this area right in here. Wait, you turned into an arrowhead, really? So that is going to be rotated around the line x equals ln of 6. Okay, so it says that we want to use shells up there. So if we're going to use a cylindrical shell, we really don't have choice, right? We don't want to use a horizontal element here because the horizontal element will hit the curve up here if you draw it there, and it's going to hit the vertical line over here. So you want to draw a vertical element at a random x, and this is a shell. Right? If you have to draw your element vertically and your axis is parallel to it, that's going to create a cylinder. If your axis and your representative element are parallel, that means a cylinder. That means a shell. So we have no choice. We've got to do it as a cylinder, as a cylindrical shell method. So we know that the area of a cylindrical shell is the area of a cylinder, so it's 2 pi RH. 2 pi r is the circumference, and then h is the height. That gives us the area of the outside of the cylinder. So now, tell me what differential we're going to have in the integral. Are we going to have a dx or are we going to have a dy? So this representative element, this representative rectangle, it's vertical. The thickness of that is dx. So that tells us, that's our clue, that we are going to be integrating with respect to x. So we're going to have a dx as the integral differential. So x is our independent variable. That tells us that we want to replace the r and the h. They need to turn into x's. If we're going to have an integral with a dx, then the r and the h have to be some expressions with x. Can't be any y's in there. So we know that. So that's just sort of some mental checkpoints. So we need to look at this and identify r, and we need to identify h. H is easy, right? H is just whatever the height of this representative rectangle is. That's the function. The function is measuring that vertical distance. R is a little more complicated. R is the distance from your element all the way over to your axis of rotation. So that is R. So here's where we have to go back to basics. A horizontal element, a horizontal segment. If you are asked how long that is, you take this x-coordinate and subtract off that x-coordinate. Right minus left. Take the right x, subtract off the left x. So that's how we find a horizontal distance. So 2 pi horizontal distance. This x value on the right is natural log of 6. The x value on the left is x. That's what we called x right there. So natural log of 6 minus x. That is the radius. And then the height is the function. So the function is the height. Does anyone have issues with that? This is the radius, that's the height. So when we go to find volume, we'll integrate from 0 to natural log of 6. And we're going to have 2 pi. Okay, let's separate this. So we're going to have 2 pi natural log of 6 multiplied by e to the negative x. And then we're also going to have minus 2 pi x e to the negative x dx. So we'll be able to separate this into two totally distinct integrals. So we're distributing. So our first integral is 2 pi ln 6 integral e to the negative x dx. That one we can do immediately. No fancy integration techniques there. But this one, that one will take integration by parts because we've got this product in here. Okay, so the first one, we get e to the negative x divided by negative 1, reverse chain rule. So we're going to get negative e to the negative x. And that's from 0 to natural log of 6. We will do an integration by parts over here where we let u equal x and dv equal e to the negative x dx. Okay, so here I've got the constant out in front. I'm not going to push it in. We'll go through the big bracket thing. So this minus 2 pi, you can always avoid the big brackets that you have to distribute through if you pull the constant to the inside. I didn't see to do that, so let's do it with the brackets just to do it that way also. We've done it the other way earlier today. So the minus 2 pi, so now we have uv on the inside, so minus x e to the negative x, ultraviolet. That's from 0 to natural log of 6. So uv minus the integral of v du. When we look at v du is negative, so that's actually going to make this positive out in front, and then we're going to have e to the negative x dx. Big bracket. So it's totally fine to leave the constant out in front. You just have to remember you're going to have the huge brackets and you have to distribute in the end. So let's go ahead. Let's go ahead and simplify this front piece since we already have separated it out here. So this is going to be upper minus lower here. So let me just write it in there and then we'll simplify it in a moment. Minus a minus is plus, e to the 0, so we have that. Minus 2 pi, big bracket. Now we're going to do the upper minus lower here. So plug in the natural log of 6, we're going to get minus natural log of 6 multiplied by e to the minus natural log of 6. Minus a minus is plus 0. I'll put it in there just so that it's clear that upper minus lower has a lower of 0. Everyone see the lower is 0? If we plug in 0 there, we'll have 0 times 1, which is 0. Now we integrate here, and we get minus e to the minus x. This also is 0 to natural log of 6. Just that one piece there. And then the big bracket closes. So when you look right here, we need to simplify that exponential expression there. And I know you see the e and the ln, and we know that those are going to undo each other. They're going to collapse because they are inverses. But we can't have that minus in front. What happens to the minus?
Exponent? No.
It becomes an exponent, right? So that minus comes up here. So if we come down here, e to the negative natural log of 6, this is e to the natural log of 1/6. Because that negative 1 flies up as an exponent, and 6 to the negative 1 means 1/6. So that's going to be how we simplify that. So this will be 2 pi natural log of 6 multiplied by. So now we're going to have negative 1/6 plus 1. E to the 0 is 1. And then over here, let's just not get rid of the bracket yet. Let's just sort of simplify what's in here first. So we have minus natural log of 6. Same thing here. This minus sign pops up as an exponent, makes that a 1/6. So this is going to be multiplied by 1/6. 0 goes away. Same thing over here. We get minus e. I'm not going to put the e. So when we put natural log of 6 right here, the negative 1 comes up. This is all going to collapse to 1 over 6 also with a minus in front. So minus 1 over 6. And then we plug in 0. So it's going to be minus, which is plus, e to the 0, which is 1. So we have all that mess. All right, let's see over here. Let's do a little distribution and try to clean things up. This is going to be minus pi divided by 3 times natural log of 6 plus 1 distributed. So that's going to be 2 pi natural log of 6. Hopefully we're going to get some cancellation. Over here, we distribute the negative 2 pi. That's going to give us plus 2 pi natural log of 6 divided by 6 here. So that's actually going to be a pi over 3. So multiplying these two together, 2 divided by 6 is a third. And then we have to, over here, negative 1 over 6 plus 1 is 5 over 6. So this over here is 5 over 6 times negative 2 pi. So 5 over 6 times negative 2 pi. I put my 5 in the wrong spot. So this part right here is 5 over 6. That gets multiplied by this. So it's going to be a 3 in the denominator because the 2 and the 6 will cancel. And it's going to be negative. So it's going to be negative 5 pi divided by 3. All right, so now we got rid of all the extra stuff. We have one nice piece of cancellation right here. That and that cancel. So we end up with a final answer of 2 pi times natural log of 6 minus 5 pi thirds. And then we can be done with that one. All right, questions on this one?
Yeah, how are you allowed to take the double negative from negative e to negative x and cancel out the negatives?
Tell me where I'm looking.
Right there.
Right here? So when we plug in natural log of 6 right there, this negative sign comes up on the 6 and makes us a 1/6, just like down there. So e to the natural log of 1/6, this all becomes 1/6, so we have negative 1/6. And then we subtract off this antiderivative evaluated at 0, so subtracting off this negative makes a positive. Plugging in 0 there gives e to the 0, which is 1.
Then how did you make the first one also a plus? One step above.
Up here?
To the left.
Here?
Yeah.
How did I make this positive?
Yeah.
So this one is coming from right here. This one is coming from right here. So this is going to be negative e to the log of 1/6. So this negative is that negative. And same thing, this part here reduces to 1/6. So this has a negative in front of it, just like this does. So this negative 1/6 plus 1 is the same as this, because this is the same as that.
Okay, it wasn't that you were taking the negative from the exponent and bring it down. It was that it was a minus,
Yes,
and then e to the negative 0, which is just 1.
correct.
Okay.
So those two things are the same. And so they both become negative 1/6 plus 1.
Okay.
Both those guys. Any other pieces there? Yeah.
Can you scroll back up to right before we did the integration? Could we take the integration by parts of ln of x minus x and e to the negative x before distributing that e of the negative
So
x?
do integration by parts right here?
Yeah,
Yes.
and that will give you the same answer?
Yes.
Okay.
Yeah, you could do this as your u right here and that as your dv.
Okay.
And that would also work for sure. Yep. Other pieces of that long and algebraically intense problem? All right, let's take a break. And if you still have questions on this, I can help you during the break. Let me see what the heck happens. Let me hit save on this recording and see what happens. We have so many recordings.
Yeah. I'll make it happen.
Hey, I love driving anyway, but it's like you just give me more time to listen to my music. Like, oh, that's how you think.
All right,
Oh boy,
integrate powers of sine and cosine.
can we not?
So if we have a product of powers with sines and cosines or tangents and secants, we have some special rules. And let's first look at sines and cosines. And there's a little multiplication in the middle there, right? So we have these two separate factors, sine and then cosine. Okay, so first off, this minus sign there, let's just rewrite this so that we don't have any negative exponents. Having a negative exponent on a trig function looks really weird, especially if it's not meant to be an inverse. So let's get rid of that negative exponent. So with sines and cosines, if one of them has an odd power, it's pretty straightforward. We pull one off and convert any that are left over. So the way I'm thinking of this is that I see an odd power on cosine. So I'm going to pull one off and put it with the differential. So I'm going to think of this sort of as a grouping over here. And the whole strategy then is to let u be the other function. We want to let u be the function that has this as its derivative. Right? So we want to let u be sine so that we can take the derivative of sine and get cosine. Now, what we have to do, though, with these leftovers is convert them to sines. So we pull one off and we convert the leftovers. If we start with an odd number and we pull one off for the differential, then we're left with an even number, like cosine squared. That can be converted using Pythagorean theorem. So this will become 1 minus sine squared of x divided by sine to the 3/2 of x times cosine x dx. And now we're ready for our substitution. So whatever we pull off is what we want to be the derivative of our u. So we're going to let u be sine of x, so that du then becomes cosine of x dx. And that works out great because all of these sines just become u's. So we have 1 minus u squared divided by u to the 3/2 du. And now we're back in familiar territory where we just need to distribute that denominator, aka split the fraction, and then use the power rule. So let's go ahead and split the fraction. So we distribute, so the u goes into the 1, we're going to get u to the negative 3/2. And then here, we put those together, and we're going to end up with u to the what?
Negative 1/2.
U to the
Sorry, 1/2.
positive 1/2. Yes, positive, because there's more u's up top. And then we do our power rule. So we'll add 1 to the exponent, so we get u to the negative 1/2. Dividing by negative 1/2 means multiplying by negative 2. And then here we add 1 to the exponent, we get 3/2. Dividing by 3/2 means multiplying by 2/3 plus constant of integration. And then we go back. So we go back with substitution. Sine of x is u, so we're going to end up with negative 8 divided by the square root of sine x minus 8/3 times sine of x raised to the 3/2 power plus c. All right, how does that look? Anything not making sense? Makes sense to me. Does it make sense to you? So all of these trig ones look way more complicated at first, but once you do the right substitution, they always turn into powers of u, which then are pretty easy to integrate with the power rule. Add 1 divided by the new exponent. Any step there not sure about? All right. We'll go to tans and secants. So sines and cosines are the easier one. Odd power, pull one off, convert the leftovers. Tangents and secants are a little more strategic. So tangents and secants. Even on secant, odd on tangent. Those are the two that we're looking for. And so this one, we could do it either way. Because we've got the odd on tangent, we could focus on that. We've got the even on secant, so we could focus on that. Now, let's think about this carefully. Whatever we pull off, we want to let u be the other function. So with secants being even, we pull 2 secants off, and we would have to convert the remaining 2 secants to tangents. So converting a secant squared. If our power is tangent to an odd, then we have to pull off a secant times tangent. So we'd have to pull off a sectan. We'd be left with 4 tangents to convert. So our choices are convert 4 tangents or 2 secants. We could do either, but it's going to be faster if we convert 2 secants rather than 4 tangents. So I'm going to pull off a secant squared. Both ways will absolutely work, but this way will be a little bit faster. So we're going to pull off a secant squared. We're left with a secant squared. So we're just sort of pulling off a secant squared, imagining it hanging out over there with the differential. Our goal then is to let u be the function that has this as its derivative. We know that the derivative of tangent is secant squared. So that tells us that, oh, these are leftover. We want to turn these into tangents. Those leftovers need to be converted to the function that we're going to let u equal. So this will end up being 7 integral tan to the 5th. Secant squared. Remember our triangle that we get from the unit circle that says this. Tangent is the height. Secant is the hypotenuse. 1 is the base. That is the triangle that allows us to see that identity super clearly. Secant squared is the hypotenuse squared, so that's going to be the sum of the squares of the legs, so that's tan squared plus 1. And so now we have everything converted how we want it, and we're going to let u be tangent. So if u is tangent, then du is secant squared of x dx. And once again, we see that once we do our substitution, we're left with just powers of u. And those are really easy to integrate. So these trig function integrals can really turn into something they're pretty straightforward in the long run compared to some other things we've been doing. So we go to our regular power rule stuff. We'll get u to the 8th over 8, u to the 6th over 6, plus c. And the only thing we have to do is go back to x. So we're going to have tangent to the 8th here. And then for the second term, we are going to have tangent to the 6th plus c. So not too bad. Just have to remember the rule. Is there any questions on this? We'll do the setup for the other one just so that you can see it. Does that make sense? Even powers a secant, pull off a pair, convert the pair that's left behind. So let's go ahead and let's grab that thing. Copy. Now there's got to be a way to paste this right away, right? Not a double click, not a right click. I just have to hold it for so long.
Could you put 2 fingers?
Say again, 2 fingers?
You could try.
Oh, what was that? Oh, if I hit that dot? What brought that dot up? Oh. All right, I didn't grab the right thing. Did that look like it was a single finger or a double finger that brought that up?
I think you just tapped the thing twice.
That was what it took?
I think so. Brought up the white dot.
All right. I don't want that. I really don't. Try it one more time. There we go. So if we wanted to set it up using the fact that we have an odd power on tangent, our strategy is going to be 7 out to the front. We're going to pull off a secant times tangent for the differential. So we're going to think about this as 1 unit. And we'd be left with tangent. We pulled off 1 tangent, so we're down to tangent to the 4th. And we did pull off a secant, right? We brought 1 secant off. So they both go down by 1. And then we would have to convert this. These are the leftovers now. And so tangent, we use the same identity. Tan squared is secant squared minus 1. So we would have secant squared of x minus 1, but that quantity is going to be squared. So now we're ready to do our substitution. Here we would do secant of theta, secant of x. And so then we're still going to be left with a bunch of u's and going forward. So either of those techniques will work on that one. But it is going to be a little bit more work here because once we put in the u's, we're going to have to FOIL that out. We would have u squared minus 1 quantity squared, so we'd get a u to the 4th, and we'd have to square it out. So a little bit more work. Oh, just a single tap brings up that little guy. Okay. Learning. Okay. So we've got this one. Here we don't have any choice. Tangent is to a half power, not an odd power. So here our only strategy is that, okay, we have this tangent to the half power. We're going to have a secant squared, and then we're going to have a secant squared that we peel off, group with the differential. So in this particular case, these are the leftovers. So we have tan x to the 1/2. Secant squared is going to be tan squared plus 1. So that's our... Now we have the integrand rewritten in the way that we can use substitution really easily. So we'll let u be tangent. So du is going to be secant squared of x dx. And that's going to convert everything nicely into u's. So we will have 8 integral u to the 1/2 u squared plus 1 du. And in order to do this integral, we'll combine our u's, so we'll get u to the 5/2 plus u to the 1/2 du. So integrating, we're going to get u to the 7/2.
Where'd you get the 5/2? Add 2, and then it's 4 with 4. Plus 1.
You see it?
Shouldn't that be 3/2?
I don't know.
Oh, no,
So when you add 2 plus 1/2,
Oh, okay, yep. No, nothing.
so 2 plus a half is 2
I was
and...
multiplying in my head.
Yeah, it's so easy to mess up your exponents. We just fly through exponents all the time. So you have to just remember that when you're multiplying powers with the same base, you add the exponents. It's so tempting to do the wrong thing. So then 2 plus a half, so 2.5, 5/2. It's the arithmetic!
There it is.
It's not the calculus!
That's the easy part.
Right?
Honestly.
So we just have to go back to our u. So u is tangent. Yeah, as soon as the exponents become fractions, if when you're going back and you're double checking your work, just go back and think, x squared times x cubed. Okay, I add the exponents as x to the 5th. Do something really basic that you know for sure, just to make sure you're adding or multiplying properly. You should always be able to go back to a simple enough example that triggers your memory, because it's so tempting to blow those. All right. Feels way easier than finding the work done and emptying a tank. Trig sub. All right, here. Now we get to some of the more complicated problems on this test. So when we're doing trig sub, couple of things to remember. There's only 3 substitutions that we ever use: sine, secant, or tangent. Those are the only 3: sine, secant, tangent. Tangent's always when we have a plus. Sine is when we have a leading 1. So 1 minus x squared, we use sine because 1 minus sine squared turns into cosine squared. when we have the trailing one, if we had x squared minus 1, that's when we use secant, because secant squared minus 1 is tangent squared. So here we know, okay, we're going to be using a sine, because it's going to be a leading one. And it becomes way more transparent if you factor out that constant. So one of the things I saw on the worksheet, which the corrections are due Thursday night by midnight, when you're doing trig sub, whatever you're factoring out to get you to the 1, remember that whatever exponent is in the denominator, or wherever you are, but most of the time we're in the denominator, that has to come with the constant. The square root one seems to be the most obvious. Oh, I'm pulling it out of a square root. Put the square root with it. And I think we had a 5/2 on the worksheet. When you pull that out, if the power is 5/2 on the quantity you're pulling out, that 5/2 has to come along with that constant that you pull out. So in this case, we're pulling out a square root. So the 196 comes through a square root, so it's going to become the square root of 196, which is 14. And then when what we're left with in here, we have 1 minus. So here there is no 196. So if you have to, it's totally fine just to do your magic bullet, multiply that by 196 over 196. That multiplying by 1 is, when in doubt, multiply by 1. So that 196 factored out to turn into that 14. We're left with x squared over 196, but we want to write it as a wrapped up square, a single square. So that's going to be x over 14 quantity squared. So now we can see really clearly, oh, 1 minus sine squared, that's going to be cosine squared. So this tells us our substitution. We're going to take that x divided by 14. We're going to make that sine of theta. Take the derivative of both sides. And then we're ready to do our substitution. So out in front, we'll just leave that alone for the time being. X squared, well, x will be found by multiplying both sides by 14, but then we have to square it, so we're going to have 14 squared times sine of theta. Dx is from this one, we multiply both sides by 14. We're going to have 14 multiplied by cosine theta d theta. We've got all that for the numerator. In the denominator, we have 1 minus sine squared inside the square root. So we've got some cancellation. That 14, we can cancel with that 14. We'll pull out the 14 squared, which is going to bring us back to 196. And then in the numerator, we have sine times cosine. In the denominator, we have the square root of cosine squared.
Why isn't the sine squared on top?
It should be squared.
It should be squared, thank you. So x squared, yeah, so that should be 14 squared times sine squared. Good call, thank you. That should be squared. Thank you. So at this stage, square root of cosine squared, technically it should be absolute value of cosine. But if we have no information about what quadrant theta is in, we just assume that if we're taking the square root of cosine that we're dealing with quadrant 1 or 4, that the square root of cosine squared is cosine. If they wanted us to be more precise here, because we know that the square root of x squared is absolute x, that sometimes it's x and sometimes it's negative x. Depends. And so if they don't give us any extra information, we don't know which way to go. We just assume that we're in quadrant 1, square root of cosine squared is cosine. They will give us extra information if they wanted us to be in quadrant 2. If we were in quadrant 2, then the square root of cosine squared would be minus cosine of theta. So if they don't give us any extra information, which they usually don't, then we just assume the best, that we can just, do that kind of thing. So square root of cosine squared is cosine. It cancels with the cosine in the numerator. So then we're left with the integral of sine squared multiplied by 196. Integrating sine or cosine squared, we have to reduce the power. So sine squared or cosine squared, it's the only power reduction you need. This is going to be 1 minus cosine of 2 theta divided by 2. So sine squared reduces to that one. Cosine squared reduces to plus. So we're going to bring this out here and chop that in half. So what do we get, 93? No, 98? 196 divided by 2, 98. And now we can integrate 1 and get theta. We can integrate cosine and get sine of the same angle. But reverse chain rule. So we have that. So the 2 underneath, that's being combined to make the 98. Now we use double angle identity for sine. Double angle identity for sine is 2 sine cosine, and the 2's are going to cancel. So we have that. Sine of 2 theta is 2 times sine theta cosine theta, so the 2's will cancel. So there's our double angle for sine. All right. Now we need to go back to x. Got to return to x. So we build our magic triangle here. So this magic triangle, always build it as if it's living in quadrant 1 of the unit circle. You can imagine it in quadrant 1. That's the best way to think of it. We want this relationship to be true, so theta is down here. Sine is opposite over hypotenuse. And then we use the Pythagorean theorem to get that this is the square root of 196 minus x squared. Now we have all the trig functions. So we will have 98 times theta. So theta we can get from the original substitution up here. That's going to be the inverse sine of x over 14. Minus, I'm going to distribute this 98 here. So then minus 98 multiplied by sine of theta, which is x over 14. We can get it from up there or right here. Sine is opposite over hypotenuse, x over 14. Cosine of theta is adjacent over hypotenuse. So that will be square root of 196 minus x squared divided by the hypotenuse, which is 14, plus c. Yeah?
So where do you get the sine theta, cosine theta again?
Double angle identity,
Oh, okay, gotcha. Oh yeah, then it's divided by 2.
and then the 2's cancel, yeah. Double angle identity. Okay, so then we can just do a little bit of cancellation, perhaps. This inverse sine piece, nothing we can do here. Let's see, 4 goes into, no, 2 goes into there 7 times. 2 goes into there 49 times. Oh, and then, it goes in evenly, huh? 7 goes in once, 7 goes in 7. Oh yeah, 70 plus 28 is 98. Okay, all right. But then this 7 goes into there twice. All right, some cancellation there.
Wait, wouldn't that still be 7 because those 2 are multiplied?
Say that again?
Wouldn't it be 7 times x times the square root?
Yes, but then that 7 will cancel in this denominator, because we have 2 denominators here. 14
Oh,
times
yeah.
14. So those 2 denominators are all going to turn into a 1/2 in total.
Hmm.
So 1/2 x square root 196 minus x squared. Plus a constant of integration. So all right. 7 times 14, 98. Should have been easier. You know you're getting tired when you just start saying, I'm going to just keep dividing by 2. I don't want to think any bigger. I'm
2's
always-
as big as you need.
Right? Go with the minimum. So any questions on any of the steps with that trig sub? Okay.
If we wanted to memorize all the double angles, because we don't have them all memorized. we just-
Say that once again.
Should we memorize all the double angle identities?
This is the only double angle that we are using. So yes, you want that one memorized. That one shows up a fair amount.
So we won't get any cosine 2 theta?
No. Yeah. No. Sine of 2 theta is the one that pops up. So the 2 double angles, so that's the one that pops up. What is cosine squared of 2 theta if you did need it? You're not going to need it on this test, but
I think it's 1 minus sine squared. No, actually, let's check it.
so that was pretty close actually.
2 sine squared theta plus 1.
The main identity for double angle for cosine is this one. And then you can convert it into the alternates by replacing cosine squared of 1 minus sine squared or sine squared of 1 minus cosine squared. So those are the 2 double angles. This is the one you need though for this test. Sine of 2 theta is 2 sine theta cosine theta.
Yeah.
How do you get those identities? Where do those come from? Anyone remember where those come from?
Triangle.
No.
No.
I mean, when you think trig, there's probably a triangle you can draw somewhere. But usually the way you develop those are by sine of theta plus theta or cosine of theta plus theta. You use those sum and difference identities. But we're not going to go through that, but that's where they come from, sum and difference identities. Okay. Another trig sub. So x squared minus 400, so the theme here is an x squared minus 1, so a difference of squares with a trailing 1. Sine, secant, or tangent? Secant. So difference of squares is either sine or secant. Leading 1 is sine, trailing 1 is secant. So this is the worst case scenario, right? All right, let's be thoughtful and careful here. So we want to create a difference of squares with a trailing 1. And we will pull out the 400 in the denominator. What is the power on that 400 that has to come along with the 400?
3 halves.
3 halves. So it's not just 400 coming out. 400 comes out with the exponent of 3 halves. And there is no 400 with the x squared, so it's going to create an x squared over 400. So that's going to be x divided by what quantity squared? 20. 20 times 20 is 400. So we will do our substitution now. So we know it's going to be secant. So x over 20, we're going to let that be secant of theta. That's our trig sub. We take the derivative of both sides. Derivative both sides, and now we're going to do our substitution. Out in front, we can do a little bit of simplification. When we have a rational exponent, the denominator is a root. So the denominator is a 2 up there, so that means a square root. Square root of 400 is 20. So we're going to have 20 cubed here. We'll just leave it like that for now. Maybe there's going to be some 20s that come and wipe out. So we have 20 cubed. dx, we look here, solve for dx. We isolate dx by moving a 20 to the other side. So that's going to be 20 multiplied by secant of theta tangent of theta. D theta. Bless you. Denominator. We end up with parentheses secant squared minus 1. All raised to the 3/2 power. So again, we're dealing with this triangle. This triangle is your friend. So secant squared minus 1 is going to be tangent squared. Out in front, we're going to be left with 1 over 400. One of the 20s are canceling. On the inside, we'll do it one step at a time just to make sure we don't miss anything. This is going to be secant squared minus 1 converts to tan squared. Tangent squared to the 3/2
Tangent 5.
is going to be what?
Tangent.
Tan cubed. So here we have power to power. When you have power to power, that's when you multiply the exponents. So 2 times 3/2 will be 3. So that's going to give us so we'll end up with a tan cubed in the bottom. One of those tangents, of course, is going bye-bye. So we have that. So, we do not have the 2 standard cases for secants and tangents, even on secant or odd on tangent. We don't have that. So if we don't have that, we have 2 choices remaining. Pythagorean theorem, you could take tan squared and turn it into secant squared minus 1. That's not helpful, though, because when you take a denominator, you prefer it to be a single term. Taking a single term and turning it into a 2-term thing is not usually the way to go because you can't split the fraction. It's fine to turn a numerator into 2 terms because you can split a fraction. Third and last possibility, turn everything to sines and cosines. So Pythagorean theorem doesn't make sense, then go to sines and cosines. And let's see where we end up when we do that. So secant is 1 over cosine of theta. Tangent is sine over cosine, but it's going to be flipped. So we're going to end up with cosine squared on top and sine squared on the bottom. So we'll get that. So this will be simplified to cosine theta over sine squared of theta. And what do we do now?
Split the fraction.
No, there's no fraction to split.
Well, we could turn it into cotangent of theta plus secant theta.
You could turn it into cotangent times secant.
Yeah, oh, yeah, sorry. Never
But
mind.
that's not, it's way easier.
Yeah.
Don't overthink. If you already have sines and cosines
So you just plug in the triangle.
Can we just use sub?
with u equal,
Sine.
yeah, exactly. Because if we let u be sine, isn't its derivative right here?
Yeah.
Derivative of sine is cosine. So if we go all the way down to sines and cosines, ideally we go with a regular u sub. That's going to be our first strategy if possible. And what we notice right away is that, oh, the derivative of sine is the numerator. And so that is going to be our key, because we see that the derivative of sine is exactly that numerator. So we can just integrate it as u to the negative 2. So 1 over 400, u to the negative 2 times du. Now we're back in power rule land. Add 1, divide by the new exponent. So we're going to add 1 and get a negative 1, divide by negative 1. So we're going to end up with negative 1 over u plus c. Then we have to go back to the prior variable, which is theta. So 1 over sine of theta, which we could write as cosecant of theta. Doesn't really matter. Could keep it as 1 over sine, because we are going to go back to x's eventually. So we've got that. So now we're back to thetas. Now we build our magic triangle. Our triangle that takes us between thetas and x's. It's our gateway between thetas and x's. So secant of theta is x over 20. Secant is x over 20. So hypotenuse over adjacent. Right? Secant is 1 over cosine. So cosine of theta is 20 over x. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. Whichever way you can remember it easiest. And then this is square root of x squared minus 400. Now we good? Okay, so any questions on any of the steps there? No simplification that we can do here, so that is our antiderivative. More correctly, our family of antiderivatives, indefinite integral.
Question.
Yes?
Don't you have to multiply the square because you can't have it in the denominator?
You can have a square root in the denominator.
Oh, okay.
That's fine. Yeah, you could rationalize the denominator if you wanted. You could multiply top and bottom by square root of x squared minus 400.
Right.
But you don't have to do that.
Oh.
The only time, once you get above pre-calculus, the only time, or even in pre-calculus, the only time we really insist on a rationalized denominator is when you're on the unit circle. And on the unit circle, we really emphasize it because we want to be able to compare the magnitudes of these 3 common numbers. And if they all have a denominator of 2, you can compare them. If they all have the same denominator, the bigger numerator is the bigger number. So square root of 3 is bigger than square root of 2, which is bigger than 1. So it makes it really easy to compare them. So usually that's the only time we really want to ensure that we have a rationalized denominator. Otherwise, it's fine to sort of... And the other time is if you have 2 square roots. Generally, if you have something like this, we don't want 2 square roots. So here, most of the time, we are going to rationalize the denominator also so that you don't have 2 roots. But other than that, it's totally fine to have roots in the bottom. You know, now that we're beyond pre-calc. So we've got our last one is the tangent one. We're going to factor out the 81 in the denominator. And what will that 81 come out to the front as? 1 over 9. Yeah, it's going to be a 9, a 1 over 9. Because if we take that out, it's coming through a square root. So that's going to be a 9 out in front. And we will be left with 1 minus x divided by... There's no 81 there, so we put 1 in the denominator. It's going to become an x 9ths quantity squared.
Or should we both?
Plus, thank you. Tangent is plus. So then x over 9 becomes our substitution. Okay, I think I want to make sure we get to the improper integration. I will finish this off right after class just to make sure. That's the setup though. Let's go one more step and then let's go to the improper integration. I want to make sure we do some review of that. So here's what our conversion will look like once we convert over to thetas. We are going to have 81 tan squared. Dx is going to be 9 secant squared. And in the denominator, we have 1 plus tan squared, which is secant squared. Square root of secant squared is secant. So that's what we would get after we substitute. Okay, so let's do some of the other ones. Make sure we get to improper. I'll go through and write the solutions to any of the ones we don't get to, but let's go to improper. That's going to be harder than PFD. So when we look at an integral and it has limits of integration, sometimes it's a definite integral and sometimes it's not. This one is obviously not a definite integral because we see the infinity symbol staring right at us. So that tells us that it's an improper fraction. And whenever we have an improper fraction, the first thing we do is write down limit. And then we figure out what the subscript should be. And in this case, b is going to infinity. So we're going to make it the limit of a definite integral. So that's always the first step. With an improper integral, you introduce the limit symbol. That comes in right away. And so the idea is that we want to take the limit of a definite integral. This definite integral is going to become a function of b. Whenever you have a definite integral with a letter in one of the limits of integration, you end up with a function. And we can always take the limit of a function. So here we're going to have limit of the following function. Well, we get x to the 1/2 divided by 1/2 from 11 to b. So power rule. Add 1 to the exponent divided by the new exponent. This is going to be limit of 2 square root of b minus 2 square root of 11. And this is as b goes to infinity. And what do we say this limit is? Infinity. As b goes to infinity, the square root of infinity is infinity. As b is going to infinity, the square root of infinity is going to infinity. So this diverges. So we say that this diverges. And if we think about this, let's go back to our sort of threshold kind of thoughts that we had before. The power on the x in the denominator is fractional. And what we have seen is that when the power on x is fractional, we have convergence if it was a vertical tail and divergence if it's a horizontal tail. This is a horizontal tail going from 11 to infinity. So if this went from 0 to 1, we would get convergence because that has a vertical asymptote at 0. Right? Division by 0 is undefined here. Yeah, if we went from 0 to 1, we would have a vertical tail. There would be an asymptote at 0. All right, let's look at this improper one. So this one is also a horizontal tail. It's going to infinity. We see that infinity jumping right out at us. So we know the first thing we're going to do is write down the word limit. So this will be the limit as b goes to infinity. Now we have a definite integral. That's a definite integral. Okay, doesn't have an immediate antiderivative, so the first thought is, can we use regular U sub? And then if that doesn't work, then we go deeper into our quiver of integration techniques. Will U sub work here? If U sub were to work, usually you want to let U be sort of the more complicated part of the integrand and hope that its derivative is present. What is the most complicated piece of this? Yes. So is its derivative present?
Yes.
Yeah. Right? 1 over dx is present. This is the derivative right there, dx over x. So that works really well. So this is going to give us limit as b goes to infinity. Now we're converting to u's here, so usually what we're going to do, because this b right here is not a u limit, we're going to usually use placeholders. So this is going to be 9. We could have factored that out. We still can in a minute. So that 9, this is 1 over u du. So we're going to write it as 1 over u du and then multiplied by 9. We have that. And we know what the antiderivative of that is. So this will be 9 times the natural log of absolute value of u with these placeholder limits. Well, we want to get rid of the placeholders. We want to go back to x, so we're going to convert back. So this will be 9 natural log absolute value of u. So absolute value of natural log of x. Now we're back to our original limits, 2 to b. Now we look on this interval, and on this interval, natural log is actually positive. So you don't really need the absolute values here. And we would end up with this limit of all of that. As b is going to infinity. And what is that limit going to be?
Infinity.
Yeah, that's also infinity. So this is also diverging. So that's infinity, so that diverges. So our rule of thumb, we have seen if the power on x in the denominator is bigger than 1, like a 2 or a 3, then the horizontal tail converges. Power of 1, it diverges. Now here's kind of in between. We have a power of x of 1, but natural log of x is increasing the denominator, but it's not increasing it enough to get convergence. Let's take a look at our our next improper integral here. What's our guess on this one? Converge or diverge? So this one, first off, is vertical. So with vertical tails, we've seen that they operate the opposite of horizontal tails. Horizontal tail, power bigger than 1 converges if it's horizontal. Power bigger than 1 vertical should diverge. Right? Because that power is bigger than 1 and this is a vertical tail. Okay? So let's see. So first we recognize that this is not a definite integral because there's an asymptote right there at 7. So here we are going to take the limit as c goes to 7 from what side?
The right.
The right. So the interval is from 7 to 8, and we need to stay within the interval. So if we're going over to the left endpoint, we're coming in from the right. So that's going to be c going to 7 from the right. And now we have a definite integral here. We are going to make this a negative exponent in the numerator so we can integrate. And we can just use power rule here. We don't even need reverse chain rule because it's just an x. So this is going to be x minus 7. We add 1, so we add 4/4. We're going to get negative 1/4. So we add 1, divide by the new exponent, so we're going to divide by negative 1/4, multiply by negative 4. We'll do it in a minute. From C to 8. So this negative 4, I'm going to pop it to the front. And then we're going to have a limit as C goes to 7 from the right. Let's plug in the 8 first. When we plug in the 8, we get 8 minus 7, which is 1. 1 to any power is 1. And then we're going to subtract off what we get when we plug in the C. So we're going to have C minus 7 to the negative 1/4. And for a lot of us, it's easier to not have a negative exponent. So it might be easier to evaluate this if we write it this way. Okay, so let's think about that. So C is going to 7 from the right. So we're thinking 7.1, 7.01. 7.001, etc. So this is always positive, correct? So we're approaching 7 from the right, that's always positive. But it's going to 0. So this part is going to 0, which means this part is going to positive infinity there, because this is always positive, and it's going to 0. So that's but 1 minus infinity is negative infinity. So this piece right here is going to go towards negative infinity. But then if this is going to negative infinity and this is a negative 4 out in front, the overall limit is,
Negative infinity.
well, negative times negative.
Sorry.
Negative times negative will bring us back to positive. So again, this one will diverge. All right, so we'll stop there. I'll fill in the blanks for the 4 that we didn't get to, so that you have all those. And I will stitch together 4 videos from our crashing computer. Why are you crashing on it now?